Hello, fellow machine learning practitioners. We all have been in this situation when the models trained on clean idealized data start falling apart when they face the real-world conditions with its noise and unpredictability. Today, we'll compare two models, a decision tree, which is a set of if-then conditions, and a multilayer perceptron, or MLP, which is a classical type of an artificial neural network, and see if both of them are capable of modeling nonlinear data, how successfully they do it, how they fail to do it, and how differently they fail. We'll learn about the importance of preprocessing data. We'll see why a sudden increase in accuracy is not necessarily good news, and how a model can confidently be wrong. So here is the experiment. What you see is a model of a railroad equipped with a Hall effect sensor that can detect an approaching train thanks to an attached magnet. When a train is detected, an ultrasonic sensor starts reading the distance, and the model deployed on the MCU makes a decision if the gate needs to be closed. In both positive and negative runs, the train may be decelerating. If the train manages to stop or sufficiently decelerate before it reaches the gate, it may remain open. Otherwise, if the train is moving too fast, the gate needs to be closed for safety reasons. So, what can go wrong? First of all, we all know that feeding raw data from the sensor into the model is not a good idea. Sensors are imprecise. They can drop values, they can produce jittery readings thanks to the real-world noise. That's why we have to apply data preprocessing. We use the hold last valid strategy to fill for missing readings. Another problem is data spikes amplified by derivation. That is, when we convert distance readings into velocities, the differences between adjacent values become even more noticeable, and they are further amplified when velocities are converted into acceleration. To even out these spikes, we apply a 3-point median filter. But even that is insufficient when we face the problem of a dataset shift. It occurs when the model is applied to the data that's fundamentally different what it has seen during the training. Here is the train that we used for training our models. It has a solid vertical front surface, smooth but not shiny. It's perfect for reflecting ultrasound. But what happens when a new model of train is introduced? Let's say a high-speed train that has an angled surface. We can't retrain and then redeploy our models on each new train in our railway system. That's too long, too expensive, and all this time the gate must remain functional. Think of extreme cases like this fantastic snowplow with a moving part at the front. The gate must respond reliably to this train as well. It's no surprise at all that both models fail on new unseen trains, but they fail differently and for different reasons. It turns out the decision tree fails to generalize completely. That's not surprising because a decision tree splits data into linearly defined regions, and it's not very suitable for modeling non-linear data, which is the pattern of an accelerating or decelerating train motion. In the table that shows the results, you will see that the decision tree performs unexpectedly well on the most challenging of the three trains, the plow train, but the high true positive rate is not a sign of generalization. Apparently, this train managed to replicate the pattern that our model accidentally learned. The multilayer perceptron, on the other hand, generalizes pretty well, which was expected, because a neural network is precisely the architecture that can model nonlinear data. Most of the failures fall into one of three categories. When the train comes too close to the sensor overshoots. It reads the distance behind the train, which is greater than the distance to the front surface of the train, and the train appears to be moving away from the sensor. Quite a few of the faulty readings are characterized by the following pattern: a number of flat distance values followed by a partial recovery or a slight uptick, which can be explained by the jitter in the sensor, thermal effects, or simply the train settling down after it has stopped. This is apparently the accidental pattern learned by the decision tree and then replicated by the snowplow train. Finally, if we inspect the logs from test runs, we'll notice that in case of false negatives, the MLP model is not uncertain, but it's confidently wrong. The confidence score it outputs is not anywhere near 50%. These failures teach us a few valuable lessons. First of all, no matter how clean and perfect your data is, preprocessing is not optional. You have to handle missing values. You have to address sudden accidental spikes in your dataset, otherwise the data you collect will be complete garbage. High true positives is not always good news, because the model can succeed for entirely wrong reasons, and high accuracy doesn't always mean that the model is capable of generalizing. The neural network's confidence on false negatives is the most dangerous failure pattern, because in this setup we're talking about safety on a railroad. This pattern needs to be addressed separately with great care. Finally, that the models fail differently gives us the opportunity for an informed choice of the model that's more appropriate for the task. The decision tree is traceable and interpretable. We can inspect the if-then statements that it's composed of to understand why this or that branch was chosen. A neural network doesn't simply output the final decision, yes or no. It can produce the confidence score that we may use to tune the model's hyperparameters for this particular task. The central question of this experiment, however, remains unanswered. What should we do about the dataset shift? What should we do when new trains are introduced? Should we increase the margins for the decision making? Or should we introduce a rule-based fallback for when the confidence level is below a certain threshold? Or should we collect the operational data in the online mode to then retrain and redeploy the models? The answers to these questions depend on factors that fall outside the machine learning domain.